step is just definition of eigenvector, nothing more. Second step, I expand the X matrix as its columns, the P columns. Then next step is I multiply out this vector and this X matrix. So this is a scalar. This is a vector of 1, for our usual regression model. This is the second element of the eigenvector. This is the P value, P element of the eigenvector. So, what do we have here? Take a look at this. So this is a constant multiplied by the vector x plus a constant multiplied by vector x2 and so on, equal to this. All right. So next is, so the next step is we examine this value, this lambda j. So let's consider lambda j to be very small, very, very small. If you have lambda j to be very small, then this lambda j multiplied by this vector, let's say it is 0.01. So you multiply by it, all these numbers will become very small. And so what you have is a zero vector, approximately a zero vector on the right hand side. Now, let's take a look. So now, if lambda j is small, then this linear combination of x is approximately 0. So what does that mean? This means we have established a relationship concerning the dependency among x1, x2 up to xp. They are related this way. Yeah? So this page shows us that if one of the lambda is small, then there will be a dependency among this. We are not talking about correlation between two random variables now. We are talking about dependency of these P vectors. So this page is very important in the understanding of multicollinearity. So the conclusion is this. If you have a small lambda j or eigenvalue, that means you will have some dependency among x1, x2 up to xp. The smaller this one is, the greater is the dependency. Okay? So if I analyze by x prime x matrix, I find that all my eigenvalues are larger than 0, much larger than 0. Then it shows no dependency. But if one of them is close to 0, then there is dependency. All right. Now, let's try to understand. So I've gone through two important pages that show you the relationship between eigenvalue and dependency or multicollinearity. Okay? So the first one, this one, shows us that the distance between beta hat and beta, or the average distance, will be large if you have a small eigenvalue. So small eigenvalue is not desirable. The second one, the second analysis here shows us that a small eigenvalue implies there is a high dependency among the columns of X. Okay. Now let's look at the data. This data here that we are going to use throughout this chapter. So this data, there is a response, and there are 3 regressor variables. Here is the conversion. What conversion? Well, in this experiment, we want to find the conversion of N-heptane to acetylene. Yeah. So this is the gas. So it's a percentage, and this number is only positive or non-negative. You can't have a negative conversion. And then it depends on 3 temperatures in the manufacturing of this gas. All right. It depends on the temperature of this H ratio. H ratio is the ratio of H2 to N-heptane, and the contact time. So there are 3 regressor variables which you can vary to study, the conversion. So what is it that we are interested in? Well, we are interested in the settings of temperature, H ratio, contact, that give us maximum conversion. So we want to know, what should we do to get maximum conversion? It seems maybe, this is it. Here, if you choose this field setting, you get the maximum conversion. Some of these are not too good. Is there any other setting that will give us even better conversion? That's the objective of this experiment. And this gas is useful. You can use it to, metal and so on. So let's try to study this multiple linear regression model. So, of course, we are concerned with multi-collinearity. So first thing to do is do a scatter matrix plot. To study the connection is to see if there's any relationship between temperature, H ratio, and the contact, these 3 regressor variables. So temperature versus H ratio, I don't see any relationship. Temperature versus contact, it seems like there is a strong relationship here. H ratio and contact, I don't see any relationship. So there is some potential problem here. So you can take a look at the correlation table of correlation coefficient. You can get this table easily by using the function COR. And it will show you that there are 2 regressor variables that are highly negatively correlated: the temperature and the contact. They're highly. Temperature and contact here, highly negatively correlated. So that's potential trouble. Well, let's try and fit the model now. See what happens. Well, the model that I want to fit is the full quadratic model. So I have the model is this: temperature, H, C, and all the interaction and the quadratic terms here. So these are the interaction, and those are the quadratic term. So that is my full quadratic model. And before I can actually analyze it using the raw data itself. But if I were to scale it, standardize it, standardize means subtract the sample mean, divide by the standard deviation, I can help to reduce the effect of multi-collinearity. So that's something we can do. If you opt not to do it, also can. But if you do it, the effect of multi-collinearity can be reduced. So let's do it. I'm following the textbook so that if you read it, you see exactly the same thing. But I'm not doing it for P. Do we need to do it for P? Not necessary. Because this reducing the effect of multi-collinearity is for the regressors. But sometimes we do it. There's one reason we do it. Do you know what reason is that? If you also standardize P, then beta naught will be 0. Okay? That's one thing. Okay, so let's fit this model now. So after we have standardized the 3 variables, you can then calculate TH, TC, HC, and so on. And you can fit the model. So I got this page from the textbook. Now let's take a look. Remember, which two variables are highly correlated? Let's go back. Is T and C. This one. So T and C are highly correlated. So let's look at the effect on the standard error. So here are all the terms of your model. These are your regression coefficient, and this is the standard error. This is the accuracy of your estimator. You can see that some are very small, 0.3, 1.6, 1.4. Those that I circle, they are big. They are bigger, of another magnitude. And which one is big? T, C. Remember, T and C are highly correlated. And because of that, all terms involving TC, T squared, C squared, they all have high standard error. They are estimated much more inaccurately than those that are not correlated. Yeah? The variance are larger. Here actually the R square is very good. Yeah? R square is 0.998. There's no, don't ask me for a cutoff point. What's the cutoff point for R square? Students have asked me that. I tell you, I can give you a model with R square equal to 0.999, and yet it's still a not well-fitted model. Okay? This is one example where R square is almost perfect and is still not well-fitted. Why is that so? If you rely, statistics, regression analysis is not as simple as give me a cutoff point. Is it good or not? Give me a cutoff point for this. Give me a cutoff point for that. We are not robots. We need our intelligence to make decisions. So, I will tell you why. But let's go through this R program to find out how we did it, how I did it. So I scaled these three. I did not scale this. The rest I obtained by multiplication and fit the model. So in case you are interested to do it using R, that's what you get. So that's what I get. So this is from the textbook. So I ran an R program. I got very similar result. If there's any discrepancy, that means there's an error in the book. Okay, not my problem. So I believe what I've done. So if you see any discrepancy, error in the book. All right. Now, why would I say that this model is not well fitted? Let's see. Not well fitted in certain sense. I'm going to explain now. So these are my response. The percentage conversion. P hat is what I got using the fitted model. So let's compare. This is what I observed, this is what I predicted. Are they close or not? Very close. It looks good. So it shows that if you do prediction within the range of experiments, it's fine. This model is good. But now let's look at this. Let's look at this. So here are the data. Here are the data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the data is collected along this, what I call ridge here. Nothing to do with the ridge regression that we are going to learn. But the data is collected here. This is where the data is. All right? So, if I have a point here, J, the observed value is 50.5. The model gives me 50.01. So the model is doing very well. Yeah? So if of all these are known, so if I have another value here, I should predict quite accurately. I have such confidence. You see, all these are very close. All these are very close at this point here, very close. Now, what if we want to do estimation beyond? Remember our objective. Our objective is to find setting of the three regressor variable to give us maximum conversion. I'm not happy with 50. You know, the existing conversion rate is only 50. So I don't go beyond. So I try out a point here with reactor temperature 1100 and then contact time here. I don't have an observed value. There's no P here, can you see? And it gives me a conversion of what? Minus 33.79. So if I try out this point, it says your conversion will be 22.15. 22.15 maybe I can accept. But if the model tells me that if I set my temperature here, my contact time here, I'm going to get a negative conversion, what do you think? I say this is rubbish. If I perform the experiment, it's not going to be minus. At worst, it's 0. It tells me it's minus 33. So you can see this model is completely useless here. Here. So this is extrapolation. Okay? So what if I want to try extrapolation here at two other values? So here, at this value, and at this value. And it's even worse. It gives me negative conversion. So this shows that the model is useless for extrapolation purposes. Yeah? It's only good within this region. So I can try to make, here also I'm a bit worried because I don't have data. In between here, maybe I'm okay. But I'm not interested here because I know maximum is here. So maybe I want to go beyond here. But it gives me negative prediction. That's totally useless. You see that? That's why I say, even if the model is, give me an R square of 0.9977, I'm not happy with it, okay? So if I give you a quiz question, if you have R square of 0.999, are you going to be happy or not? The answer should be not necessary, okay? It depends. So the conclusion for this particular data is the fitted model seems satisfactory for prediction within the range of experiment, but definitely not satisfactory for extrapolation. All right. So now another way to do it is to do unit length scaling. So here I scale everything, and then after I scale, I find them, and then I scale them again. So this is the usual way of scaling. You find P, T, H, C scale, find all these terms, interaction, square, quadratic term, and then scale them and fit the model. If you fit the model this way, will it help? Now we are talking about a standardized model, and so one is from the textbook, this one is from the textbook, this is from the R program that I ran, so you can see that they are actually the same. So if you read the book, you can actually check it with your R program. Yeah? And you can also find the x prime x matrix of the unit length scale variables. The x prime x will be a matrix of correlation. So you can study which is correlated with which one. Huh? Okay. Now I'm going to go on. What have I done? I show you two connections between these eigenvalues and multicollinearity. And then I show you one example. Now let's study the sources of multicollinearity. One is data collection method. One is because of the constraint of the model. Third is model specification. Four is an overdefined model. So remember this delivery time example. You know, you deliver cases of soft drink, and this is a distance traveled, and this is the data collected. You can see that there is a high correlation between distance and cases. So when you run this multiple linear regression model using these two regressive variables, there'll be trouble because there is high correlation. So what you need to do is collect data to break this correlation. Collect some that you have high cases but short distance, or small cases but long distance. Yeah? If you can do that, you can see that the correlation now will drop to a much smaller number. So you can vary your data collection method. Well, the second one is multicollinearity exists because of constraint on the model. Look at this example. I think It should be quiz time now. Let me check. I give you a quiz now. I wonder why my alarm doesn't ring. Let's see. Maybe I said it wrongly. Okay, let's do it. All right, I think it's on now. Let me let you do the quiz first now. Okay, the quiz is very simple, and do it. Take a short break. I like to start at 10:55. Okay, at the end of the quiz.
So if this is messy,
So you have 5 minutes rest from now. And try and break it or reduce the correlation by collecting data here and here. If you can do that, then you have at least solved the problem of multicollinearity for this one. But sometimes this model, for example, we have this model. Here is the family income. Here is the house size. Yeah. So if you have a small house size, that means usually you are not doing too well. That's why you bought a small house. Usually, I mean. If you have a big house, quite likely your family income is large. So this is inherent in this relationship. And so there's a strong correlation between these two regressor variables. Can we break it by trying to find a point here, maybe a point here? Well, to get a point here means what? You are asking for someone with low family income. You are looking for someone with low family income to have a big house. This is very rare. Not easy. Or you want someone with a very high income and live in a very small house. 3-room HDB flat. And this guy is a multi-millionaire. Would he stay there or not? He won't. Yeah? So this is something inherent in the relationship and you can't change it. So the correlation stays. We can't remove it. So we need other ways to deal with this type of problem. Well, another way is you can use this model, or you can sample it, to reduce the effect of multicollinearity. Note that there are two ways. The correct way is the one that I put a tick, and that is the incorrect way. Okay? The second way actually won't change anything. The correlation will remain the same. So centering helps. Here's a simple justification. So here's my x variable. Here's x squared. So it's very high. What if x2 is scaled, and then I take x2 here, square. And then you can see that if I scale it, the linear term and the quadratic term have small correlation. So you can do that. The fourth reason is you have too many regressor variables than the observation. Then you have an over-defined model, and that's when you have multi-collinearity problem. Okay? So today I show you two ways to understand the relationship between eigenvalues and multi-collinearity. Here, of course, before that I gave you a review, and then we study using acetylene data and study the sources of multi-collinearity. All right, now I'm ready to go on to chapter 4b, 8b. Now in 8b, what I would like to do is to look at the diagnostics. So how do we detect multi-collinearity? There are three methods here. The first method is based on examination of the correlation matrix, because if you examine this correlation matrix, any two variables that are highly correlated, well, means multi-collinearity. Or you can look at the variance inflation factors and eigen system analysis of X prime X. So three major ways of doing things. So let's see. Now, examination of correlation matrix is very simple. Just look, see which one is highly correlated. For example, the acetylene data, T and C are highly correlated, negatively. It doesn't matter. So this example, you have three regressor variables, and you can see that contact and temperature are highly correlated. So it causes problem, as I've demonstrated to you. But this method is actually quite naive. It will fail in some situations. In fact, in many situations. So some researcher called Webster's, three of them, Webster, Gunz, and Mason, in 1974, came up with simulated data to demonstrate this point here. So what did they do? Well, they generated a data. There are 6 regressors in their data set. The first 4, 1, 2, 3, 4, are related by this relationship. If you add them up, 0 plus 0 plus 0 plus 10 is 10, right? So it's 10. For observation, 2 to 12. While observation 1, if you add up together, it will be 11. So what that means is there is a strong dependency among the 4 variables. If every row follows this, including observation 1, then we have a perfect relationship, perfect dependency. Here, only one of them doesn't satisfy this relationship, so there is a high dependency. So that's how they create high dependency, but not perfect dependency. Now, 5 and 6 are just randomly created, and it does not depend on any one of them. So this data set is such that the first 4 are highly dependent. The last 2 are totally independent. So can we detect this dependency using or by examining the correlation matrix or not? Well, let's take a look at the X prime X matrix for this example. So this is the X prime X matrix for this example here. You look at the correlation, none of them is big. But we know this data set, there is a strong dependency among the first four. Nearly perfect dependency. Yeah? But you can't detect it using correlation. So this method fails. Okay? So let's go on to the second method. The second method I have already described to you earlier. So here is just a quick review. So the main diagonal elements of X prime X inverse are known as the variance inflation factor. Yeah? For example, CJJ is 1 over 1 minus RJ squared. Where RJ is a R squared, when XJ is regressed with the remaining K minus 1 regressor variable. So if there is a relationship between XJ and the rest, then this will be very large, closer to 1, and then you will have a large variance inflation factor. The diagonal element will be large. That's what it is. So the second method is to examine the diagonal elements of X prime X. And these are called variance inflation factors. So I've described this before. So that's all I'm going to say. You can read this here. So where is the okay, I think I will look at this. We'll apply to this problem first, this acetylene data. For the acetylene data, I'm going to look at the variance inflation factor, XPX inverse. So the diagonal elements, okay? Look at the diagonal elements. And you can see that here we have a large diagonal element. The second one, small. The third one is large. It corresponds to this. The fourth one is small. This one is large. It corresponds to this. So you can see that if the variance inflation factor is large, then there is evidence of multicollinearity or dependency. So here is what we have seen earlier, and they corresponds to the variance inflation factor. Right? So in R, there is a function called VIF. You fit a model, VIF, fit the model. It will show you the variance inflation factor. See, some are very large, some are small. Those that are large are associated with large standard error of the regression coefficient. Okay? Well, next, let's take a look at this one. So some of you will say, I'm not going to center my data, too much trouble. So let's take a look. This is acetylene center. These are the VIF. Look at the uncentered data. The VIF are all very huge. So you can really reduce the variance of the regression coefficient simply by centering. Yeah, see? Of course, some of them still stays big because there's an inherent relationship that you cannot get rid of. How do we deal with it? Well, that will be chapter 9c. That's the most interesting chapter of this module, I think. Now, let's go back to Webster, Goose, and Mason data. You know, for this data set, it was artificially generated so that the first four regressor variables are highly dependent. There's a very strong relationship. And if you look at the correlation matrix, you won't get any hint of relationship. But if you look at the VIF of this 6 regressor variable, you will detect something. Something is wrong. You see? X1, X2, X3, X4. Very high variance inflation factor. These two, very low. So that shows that there is probably some relationship, that exists. How is it? We don't know. Of course, here we know that the first four are highly correlated. All right. Now, let's go on to the third method of finding or detecting multicollinearity. So, and the third method is based on eigenvalue analysis. So this is what we have gone through. This is the expected square distance between beta hat and beta here. And we find that it is sigma squared times the sum of the 1 over lambda j. And these lambdas are eigenvalues of x prime x matrix. So from here, we know that eigenvalue can be used to measure the extent of multicollinearity. If you just given x matrix, find x prime x, and then find eigenvalues, and then just examine the eigenvalues. If you see any small eigenvalues, that means there's a high dependency among the regressor variables. Just by looking at the eigenvalues. So this page tells us the same thing. So if any lambda is small, there will be dependency. So the third diagnostic is then based on this, based on eigenvalues. So given an X matrix, find X prime X, find the eigenvalues, and then calculate the condition number here, which I define as lambda maximum over lambda minimum. So lambda maximum is the maximum of the eigenvalues, and lambda minimum is the minimum. After that, we look at this condition number, and it will tell us whether there's any problem or not. If condition number is less than 100, there's no serious problem with multicollinearity. If it is between 100 and 1000, there's a moderate to strong multicollinearity. Anything more than 1000, severe multicollinearity. So the third method is based on eigenvalues. And then you can check each one of them. This is not the minimum, but for each one of them, you can calculate the condition indices. Any condition index greater than 1000 means no near linear dependencies. So the third method, so what's the first method? Check the correlation coefficient. What's the second method? Look at the variance inflation factor. That means the diagonal elements of x prime x inverse. Third method, look at the eigenvalues. So how do we find eigenvalues? Now all this beautiful theory, if we cannot apply it, it's useless. But R is so useful. For R is as simple as this. XPX is our x prime x matrix. You know, from the x you can get x prime x, right? Then you just say eigen. Eigen is the function that will allow you to do this decomposition. So I assign to DEC. So eigen, apply under this, it will find all the eigenvalues and all the eigenvectors for me. I store them here. If I want the eigenvectors, I just extract using this. So this, and then I do a display of all my eigenvectors. 1, 2, 3, and so on. So there are 9 eigenvectors for the acetylene data. And what about eigenvalues? To extract the eigenvalues, I just say dollar values and then display. See, these are all my eigenvalues. I can find the condition number, condition index. See, this is huge. There's multi-collinearity problem with the acetylene data. And then the condition index. Yeah. So, so this is how you can apply the third method to detect multi-collinearity. All right. So, is there any small eigenvalues? Let's take a look. Look at these eigenvalues. For this acetylene data, this is 10 to the power minus 4, approximately. Yeah, very small. This is also very small. This one, 0.01 something, small. So the condition index for this is this one. I hope I got it right. And this one is this. So at least there's one potential problem. It's much greater than 1,000. Yeah. So the condition index. So remember, if you want to use R, this is the function to use. It's called eigen. Yeah. All right. So now let's take a look at the relationship. Let's take a look. So here is T, the matrix T, which contains the 9 eigenvectors. This first eigenvector, second, third, fourth, fifth, sixth, seventh, eighth, ninth. And then I'm going to multiply this eigenvector by x. And this is what I get. The first column, second column, and so on. What am I looking for? Well, according to this analysis, x times the eigenvector is this one. And I want to see whether this one is it close to 0. So I'm looking for vector of 0. If I see any, so if I look at this, the product of these two, and if I see any column that are very small, then there is evidence of dependency. So let's take a look. So this is x times t. So this is x times the ninth eigenvector. So see this one. So I'm looking at this. I want to see whether it is 0 or not. So what do you think? Is this 0? So these are very, very small. Look. Nearly 0. At least up to the second decimal is all 0. So x multiplied by the ninth eigenvector gives me a column that is nearly 0. That shows what? According to our theory, there is certain dependency among the x columns. This is also small. Maybe not as small. Also nearly 0. This one also. There are few potential candidates. But this one definitely is according to condition in index. If you look at the other one, the first one, you can see that this is definitely non-zero. Yeah. So not this one, sorry. This one. The first one. So the first column, this is definitely not 0. But if you go further to the right, you will see that there is a near 0 vector. Because when you apply this eigenfunction, the eigenvalues are sorted and it decreases towards the end. So the last one show you the worst case. Yeah. So here we have evidence that there is dependency. Now let's look at this Webster, Gunz, and Mason data. Remember, this method, it fails for, the correlation matrix. You look at the correlation coefficient. That method fails to detect the dependency in this data set. Variance inflation factor works. How about eigenvalue? Will it help us to find dependency among the 4 variables or not? Well, it's very easy. All we have to do is to find the 6th eigenvalue first, and then look at the condition number. Maximum divided by the smallest is 2,188. So it shows there is multicollinearity problem, severe multicollinearity problem. Okay? And so this method also works for finding potential problem. Finally, if you look at this situation, you can actually try to recover a certain relationship by assuming these two to be near 0. Yeah, these two quantity. You can try to establish a relationship. It may not be exactly the same as the one that generated this data, but it does show you the possible relationship among the 4 variables. Yeah? Okay? So let's see. So today, in the second half of the lecture, we study 3 ways to find multicollinearity One is examination of correlation matrix. This method is very simple. It fails. It works very well when a pair of variables are highly correlated, but it fails when you have more than two. It may not work. For example, the Mason data. The second method is variance inflation factor. So look at the x prime x inverse matrix, look at the diagonal elements, look for large diagonal elements. That will show us whether the data, whether there's multi-collinearity or not. A more sophisticated way, or the most sophisticated way, is through eigenvalue or eigen system analysis of x prime x. Look at the eigenvalues. So these are the three ways to do it. All right? Okay. So I think the next lecture I find the most interesting. We will see how we can deal with, how do we deal with multi-collinearity. Sometimes it's inherent in the problem, like the family income and the size of the house. There's no way you can collect points to reduce the correlation coefficient. So how do we deal with it? Well, a simple way is just to remove, if you find two that are highly correlated, remove one of them. But sometimes this is not a good method if what you drop is an important variable. So we need some very advanced way. One is ridge regression, and one is called principal component regression. Okay? So principal component, I think, is quite abstract. So I hope you will be here to listen. At least it will make your life a lot easier when you read it at home. Okay, that's all for today.
Actually, you are right. So you just continue taking a picture.